Okay, let's go ahead and get started with week number 3 of ELTEC 213. There's one thing that I want to make clear to the folks that are doing the course online as well as the folks that are here in class, and that is that the lecture notes rather that I've posted online do not coincide with every single word and example and problem that I'm going to put on the board. Now that's intentional. The reason is because it would just be totally repetitious. If I just stood here and copied the lecture notes onto the board, there'd be no point in standing here and listening to me other than the comments that I would make. Okay, so there's diversity in that the textbook doesn't exactly match the lecture notes, which don't exactly match the video, but if you look at all 3 of them together, right, then you should have a good mastery of the material, right? That's been my experience on how, the best way to teach a class is. All right, so let's go ahead and start off with some examples today. Yesterday we talked about loads that were connected in parallel. Today we're going to just stick with loads that have only one resistor in them, and we're going to use Ohm's law to solve for the different quantities that we've learned about in this class. Okay, so for our first example problem, example number 1, this is what we're going to be given. We're given a circuit that consists of a DC battery. Polarity is positive on the top, negative on the bottom, obviously. And that battery is connected to a load, and that load is shown as a resistor on the board. Okay? Now, that load could be one of many things. It could be a space heater that heats up your feet when it's cold. It could be the resistance inside of a hairdryer. It could be anything that has heat that's dissipated when you turn it on. And probably, as you've experienced in life, just about everything dissipates heat when you turn it on. Okay, unless it's some little microcircuit or something. And it's still dissipating heat, it's just that it's not enough heat for you to feel it. So let's say that this load right here has a value of resistance that's equal to 150 ohms. Okay? And again, when I say resistance, what is resistance? Opposition to current flow. So what this is doing in the circuit is it's opposing the battery's attempt to push valence electrons through the circuit. Okay? Second issue, direction of current. Now in this class we talked about the concept of conventional current and electron flow, and I told you that I was going to teach electron flow. So keeping that in mind, that we're focusing on electron flow, which direction would I point the arrow to indicate the direction of current flow? Leaving the negative terminal of the battery. So the current is going to flow like this. Okay? Now, to have any circuit that is going to operate, in other words, let's say that this is a space heater, and that this is something that's warming up Grandma's feet when she's cold. Okay? In order to have any circuit that is going to operate, you have to have a closed loop. In other words, you have to have something that creates an electrical pressure. We have that, it's a battery. Okay? You have to have a connector between the thing that creates electrical pressure and your space heater. Okay, that's a piece of wire. And then you have to have another piece of wire going from the other side of your space heater back to your battery. Okay? So this would be considered a closed loop. Right? An example of an open loop would be if we took a chunk of wire out of that loop right there. All of a sudden the current would stop flowing and the heater would go cold. okay? But just to get back to our original problem where we have a closed loop, let's assume that the battery has a value of 10 volts. So there's a 10 volt battery driving 150 volt ohm, 150 ohm load, okay? And what we want to do is we want to find several things. The first thing that we want to find is we want to find how much power is dissipated in the load. Okay? And does anybody remember what the unit on power is? Watts. Right, watts. So we want to find out how many watts are dissipated in this load. Okay? Now that's going to do several things for us. Number one, it's going to tell us how much money it's going to cost us to run this load. Can anybody think of another thing that that's going to do for us if we know what the power rating on this load is? Yeah. Right. It can help us work backwards to figure out the formula. The thing that I was thinking of, and I don't expect you to read my mind, but the thing that I was thinking of was, how beefy do we need to make Grandma's space heater? In other words, can it be this big around, or does it have to be this big around, right? In other words, how big does it have to be in order to be able to dissipate that many watts? The other thing that I wanted to find in this circuit right here is how much current is actually flowing to the load. Okay? And again, we can use Ohm's law to figure these quantities out. So if we move up to the upper part of the screen here, if we look for a formula in the Ohm's law wheel that says power is equal to something in terms of voltage and resistance, what formula do we see?
E squared divided by resistance.
E squared, which is voltage squared divided by resistance. Does everybody see that? It's really important that you're able to find that in your Ohm's law wheel, which is in your book. And if you don't have your book, you know, open up your book next, or share a book with somebody. If you don't have your book open your book to the appendix. It should be at the very back of the book, and it has all of the Ohm's law formulas. Okay? So if we plug the numbers in for this Ohm's law formula, what's the value of voltage that we're going to plug in for E?
10 volts.
10 volts. So we've got 10 volts, but what do we have to do before we proceed? We have to square it. So the standard way to square it is put parentheses around it and then raise it to the second power. That way there's no confusion about what you're doing. Okay? And then obviously we have to divide that by the resistance of the load. And what did we define the resistance of the load to be? 150 ohms. So this is 150 ohms. And who has a calculator and can tell me? And I want you to get in the habit of using your calculator, even if you can do it in your head, because very soon you will not be able to do it in your head. What do you get? 0.666 watts. Okay? So the power that's dissipated by that load is equal to approximately 7/10 of a watt. A little less than a watt. Okay? Now what if I wanted to express that in milliwatts? What would I have to do to the decimal?
You'd have to move it 3 spaces back.
Three spaces, And would I move it to the right or to the left?
Oh, to the right.
To the right, because milli is going to be a bigger number, right? So if I move this 1, 2, 3 spaces, then that's the same thing as 666 milliwatts. And that's typically how that would be expressed. Okay? Either one of them is equally correct mathematically, but sometimes on exams in here and also aptitude exams that you'll take for companies, they may ask you for the answer in milliwatts, and you've calculated it in watts, so you have to be able to do the conversion. Okay? All right. The second thing that we wanted to verify was how much current would be flowing in the circuit. Now, can anybody tell me why we would be concerned with how much current would be flowing in the circuit? Right, for your load, so your load would be beefy enough to be able to handle the current flowing through it, and the same thing for the wire. Both are the same, size of the wire. In other words, if I have, obviously we're not going to have a lot of watts, a lot of amps here, but let's just say hypothetically I had a circuit that had 600 amps flowing through it, and I had a 28 gauge wire. Those are like the telephone wires, you know, that are multicolored, right? How long is that wire going to be able to carry 600 amps? Not long. It's just going to be like a fuse, just going to go. Okay, so it's very important because the National Electric Code requires that if we're going to put wiring into a house or any kind of a residential complex, commercial complex, industrial complex that's going to have people in it, that we don't undersize the wires. Because if we undersize the wires, not only do they fuse in some cases, but what else can happen? They can arc and spark, and what causes? Right, fires are caused by arcs and sparks. So very important to understand current because it's a safety issue. Okay, so again, if you look at your Ohm's law formula wheel, okay, and you want to find out what current is equal to in terms of volts and resistance, what is it? What's the formula? Current equals what?
Current equals P over E.
Current equals volts over resistance.
But we have P and E, or I guess we can do that.
You could also use P, but let me tell you why you would be better off using E and R. The reason you would be better off using E and R is you have a nice even number here. You also have a nice even number here. This number is rounded off. So by using P to calculate I, you would be introducing some error. Okay, but it would still be valid. You just have to realize you're introducing some error. Okay? Okay, so all you do is plug those numbers in. So the voltage is 10 volts. And the resistance is 150 ohms. So what do we get for the current that's flowing through our space heater circuit?
0.066.
0.066 amps. Now, if we wanted to express that in milliamps, how would we go about doing that? We would move the decimal 3 places. Which direction?
To the right.
To the right. So our decimal would go 1, 2, 3. So that would be the same thing as 66 milliamps. And that would be the current. Okay? Now, this is a very small current. This doesn't take a very big wire. Okay? But the process that we use to figure out the current that would be flowing in a circuit that would have thousands of amps is the same process. Same formulas, same process, same calculator, same everything. Okay. Let's talk a little bit about getting power to a load that is some distance away. Okay? So I'm going to move over here to my next board. Excuse me. Let's assume that we had a big DC generator. Let's say that this thing put out 600 volts of direct current, DC. Okay? And let's say that we were driving a pump motor for an irrigation system. And let's say that that pump motor was on a piece of property that was a fairly large piece of property, and we were going to have to run cable 2 miles, okay, to this pump motor. And let's just say that that this power that we had was coming from some photovoltaic solar panels. Okay, otherwise you'd probably use AC. But you could argue that if you had solar panels, you know, and they didn't cost you any money to run, why would you pay a bill to the power company if you had solar panels? Okay, so this is a practical example because we're going green, right? Okay, so
600 volts coming in from your solar panels?
sure, absolutely. So if you have different parallel and series configurations of solar panels, you can get way over 600 volts.
They could run 220 off that sucker pretty good.
Right, but it's just that your load would have to be designed to take either DC or AC. You have to do things to your load. You can't run any load on DC or AC.
Okay.
Your load has to be
So the solar panels have to be converted from DC.
No. The solar panels put out direct current.
Yeah, they have to be
Okay.
converted from DC to AC.
Right, but in this particular example, I'm just showing an example where we're not going to do that. Okay, we're not going to convert it to AC, and the reason is because the pump motor that we have runs off DC. Okay, and you can buy them. You can buy pump rotors that run off DC. Okay, so this is a long stretch. This piece of wire stretches a long way, and as a result, it's got some resistance in it. Okay, because if we actually measure this distance right here, this is 2 miles. And if we got 2 miles of cable, even if it's fairly large cable, say it's double aught cable or single aught cable, it's pretty big around, okay? It's going to have some resistance. And the manufacturer of the cable is going to usually designate the resistance in ohms per 10 feet, or ohms per 100 feet, or ohms per so many feet, okay? Then over here is our pump motor. Okay, so what I'm going to do is I'm going to draw a box to represent our pump motor. I'll just write pump. And inside the pump, there is some opposition to current flow because the pump gets hot. And as a result, it turns out that there's resistance inside of the water pump. Now, what we want to do is we want to figure out how much money we're wasting in locating our DC generator, or our photovoltaic solar panels in this case, 2 miles away from the pump. Okay? Let's say that our pump has a resistance that's equal to 100 ohms. Okay? And let's just say hypothetically that the resistance of our wire is equal to 17 ohms. For the entire 2 miles. Yeah. So in other words, what I'm doing is I'm using what's called a lumped parameter model, where I'm taking the whole 2 miles of resistance and I'm lumping it into this one little space. Okay? Thanks for asking that question. Yeah. So that whole 2 miles of wire has a resistance of 17 ohms. In other words, if you were to put an ohm meter here and an ohm meter here, and you had a guy standing in the middle, that's what he'd measure, 17 ohms. Okay? But we're just lumping it into one space for ease of analysis. Okay, first of all, let's figure out what the current is that's flowing in this circuit. Now, there's something that we haven't talked about yet that I have to show you before we can do that, and that is what happens when you have more than one resistance in a load, in a circuit. In this case, we have the resistance of the wire and we have the resistance of the pump. Okay? So what we have to do is we have to draw what we call an equivalent circuit. A circuit that basically combines the resistance of the wire and the resistance of the pump into one resistance. Okay? These two resistors, based on the way that they're drawn here, are connected in a certain configuration. And you only have a choice of 3. Series, parallel, or a combination of series and parallel. Any idea what combination these are connected in? Series. They're coupled together. They're not back to back. Okay? This is series. This is parallel. Okay? So what we can do then is we can write the equation for series connected resistors. So the resistance total, when we have 2 series connected resistors, would be equal to the resistance of the 17 ohm resistor plus the resistance of the pump. And clearly, that's going to be equal to 17 ohms plus 100 ohms. Okay? So when we combine those, we're going to get 117 ohms. So if we were to draw an equivalent circuit, question?
We would have calculated the ohms for the wire coming back too, right?
Right. Very good observation. Very good observation. I neglected the wire coming back, and that's an extremely good argument, because how is it that the wire coming back is not going 2 miles the way that I've drawn this thing? Right? So what I'm going to do is I'm going to stick in the resistance of the wire coming back, because Aaron pointed out my error. And errors are good because they keep me on my toes. Okay, so the resistance of the wire that's coming back is, we're going to say, also equal to 17 ohms because we're using the same wire. Okay? And so the total resistance of the circuit is going to be equal to the resistance of the wire on the top plus the resistance of the pump plus the resistance of the wire on the bottom. And clearly, that's going to be equal to 17 ohms plus 100 ohms plus another 17 ohms. Now, if I wanted to sidestep your question, I could have said, well, what I did without telling you is I lumped the resistance of the bottom portion of the wire into the top. Okay? But I really didn't do that. Okay? Okay, so what you can see here is the formula that's used anytime that you have resistors that are connected end to end or in a series configuration. Now, the definition of a series configuration, and this is very important, the definition of a series configuration is that the current is the same through every component. That's your acid test. In other words, if you can ask yourself that question, and the answer to that question is yes, then they're in series. Okay? So if we look at the current that's flowing in this circuit, would it be reasonable to say that the current through every component has to be the same? Yeah, because there's nowhere for it to branch off. Like in a water tee, you know, you got water coming in, and you can have water going out this way and water going out this way. Okay? With a water coupling, you got water coming in and you got water going out because you're coupling two pipes together. That's like a series connection. So if you got 5 gallons per minute of water flowing in this pipe, you got 5 gallons per minute of water flowing in this pipe. Same thing in the circuit. If you've got 10 amps flowing here, you're going to have 10 amps flowing here. You're going to have 10 amps flowing here. You're going to have 10 amps flowing here. You have 10 amps flowing everywhere. Okay? That's the definition of a series circuit. The current is the same in all components. That's going to for sure be a test question in here, be a question on the final, and be a question on probably most aptitude exams that you would take in industry. Okay? And they'll usually ask it something like this. The current flowing in a series circuit is always the same in every component, always different in every component, sometimes different in every component, really can't tell. You know, that's, and so of course A would be the correct choice. Always the same in every component. Okay, so if we add these up, what do we get for the total resistance of the circuit? 134. So we got 134 ohms. Okay, now what we're going to do is we are going to draw this circuit in a reduced form. We call it an equivalent circuit. So I'll put it here. Equivalent circuit, abbreviation. The equivalent circuit is going to have one source of energy, which is our battery. That's our 600 volt photovoltaic array that generates DC current and DC voltage or direct voltage. And rather than having 1, 2, 3 individual resistors representing, you know, one piece of wire, the pump, and another piece of wire, we are going to have one single resistor which represents all of them. The reason that we can do this and get away with it is because when we add series resistors, we simply add them algebraically. You know, 10 plus 10 plus 10 is 30. Right? And so what would the value of this equivalent resistor be for this circuit? 134 ohms. Do you see how much easier it is to analyze this circuit than this circuit? This circuit's smaller, there's less components, it's just less work. Okay? Now, if we wanted to figure out what the current was that was flowing in this circuit right here, and we know the voltage and the resistance, would it be possible to use the Ohm's law formula wheel to get a formula so that we could figure out the current? what would that formula be? Current is equal to voltage divided by resistance. The voltage would be 600 volts. The resistance would be 134 ohms. What do you get when you take 600 and divide it by 134?
0.746 amps.
Try that again. 600 divided by 134.
4.48.
Am I getting consensus on 4.4 amps? Okay. So that's the current that's flowing in this equivalent circuit. Now, you're going to test your understanding by answering this question, either in your own mind or out loud. I don't care. If the current flowing in this circuit, which is equivalent to this circuit, if the current here is 4.4 amps, what would the current be flowing in this circuit? It's the same. That's the beauty of equivalent circuits. 4.4 amps. If it's a series circuit, and remember, series circuits have the same what? Current flowing everywhere. Right. If there's 4.4 amps flowing here, how much current is flowing through this wire? 4.4 amps. How much current is flowing through the pump? How about here? Right. Okay. Becomes redundant. Okay. So we know now that there's 4.4 amps flowing in the circuit. Okay? Now, if we wanted to figure out what the total power was that was being dissipated by the pump, okay? In other words, we want to find a formula that says, I'm going to draw a little squiggly line here to separate the board. If we want to write a formula that has power in terms of voltage and resistance, what does our Ohm's law wheel tell us the formula is? E squared over R. E squared divided by R. And E squared is 600 squared. Remember, we want to put 600 in parentheses and square it, divided by 134. Whoops. 134 ohms. Okay? And this, of course, was volts. So what do you get when you take 600 squared and you divide it by 134? 448 watts. Are we getting different numbers?
I get 2640 watts. Or 2686.
I don't have a calculator and I can't do that one in my head, so you guys got to help me out. Put in 600 in parentheses, square it, hit the divide sign, put in 134, press enter. 268 watts, approximately, right?
I think it's 2640.
2,640.
Or thereabouts.
Yeah, the number seemed a little bit small. Okay, so do we have some consensus, or do we need to bring me a calculator?
Yeah, it's around 2,000.
Okay, so it's 2,000. The answer is 2,600 and what?
86.
And 86 watts. Now, is that a valid method? Is that a formula in the Ohm's law wheel?
Yeah, but you get a different answer if you multiply amps times volts. E times I. Oh, equals VA.
Okay. So we're talking about apparent power.
E times I. Yeah, that's what it says here on the wheel. You get a different answer. It's off by about 40 when you do it that way.
It's off by 40 watts.
Yeah. I think it's because we rounded it.
Oh, okay. Yeah.
It's because you rounded
Yeah.
it.
Yeah. If you, that's one of the problems anytime that you round something. If you use another formula, depending on which formula you use and which numbers you use, you're going to get some error. Okay? The error that we're getting here is like what, less than 5%? So we don't have to, yeah, about 5%. So we don't have to worry about it. But that's the source of the error. Okay? You can use either formula. Just understand that if you're using a number that's been rounded up, you're going to get some error. Okay? You just have to know that you're getting the error and know whether or not it's an acceptable error. So since we've already gone with this, we'll stay with it. All right. Now, if we go back to our original circuit, how much current is flowing through the pump? 4.4 amps. Okay? And the resistance of the pump is 100 ohms. So now we're going to use that other formula. If we want to know the power that's absorbed just by the pump, and we want to know it in terms of current and resistance, what formula do we use?
I squared times R.
Power is equal to current squared multiplied by resistance, which is equal to, in our case, 4.4 amps multiplied by 100 ohms. Just running out of room, that's why I'm not writing the units. What do you get when you do that?
1936.
4.4 times 100.
Is it 4.4 squared?
Oh, thank you.
Squared times
Thank you. 4.4 squared. Thank you. 1936. That's equal to 1936 watts. So 1,936 watts. Are we all in agreement on that? Okay. Now, I want you to note something. If we look at how much power we're losing in this resistor, or this piece of wire right here, it becomes significant. Why? Because it's so far. It's 17 ohms. It's running 2 miles. Okay? So if we want to know how much power we're losing in these resistors right here, how can we figure that out? Well, let me walk you through it. When we came down to the equivalent circuit, did we find out how much power the load was absorbing, the total load? Would that be the same as the power that the solar panels are delivering? Yeah, if you ignored these wires. Say they're trivial. Okay? So we have 2,686. 2,686 watts that's being delivered. This is the power from the source. Okay? 2.686 kilowatts. Okay? We also know that the power that's being absorbed by the water pump out here is just shy of 2,000 watts. It's 1,936 watts. Okay? There is a principle in the study of electricity called superposition. It's a fancy word for nothing more than adding things up. Okay? The power here must be equal to this power plus this power plus this power. That's superposition. In other words, if you add all the powers up, they have to be equal to the power that the source is generating. Okay? So, if we have 2,686 watts that we're generating, and our water pump is eating up 1936 watts, then how many watts is being dissipated, are being dissipated in our forward and our return wire?
750 or 375 each.
Well, let's look at it mathematically, right? All we'd have to do is take 2,686, right, minus what our water pump is using, 1936. And those are all in watts. Is that how you did that? And what did you get?
750.
750 watts. Now, compared to how much power the pump is using, around 2,000, if we're dissipating just less than 1,000 in the cable, would you say that's a very efficient setup? No. That would be something that you would want to throw in the trash. You would never want to build that. You would come up with another design plan. Okay? And there's a lot of other ways you could do it. One way would be you could buy an inverter, you could step the voltage up, and then by stepping the voltage up, you would reduce the line losses. Because by stepping the voltage up, the current decreases in direct proportion. Right? So if the voltage goes way up, the current goes way down, and then the power, which is equal to I squared R, that's the power lost in that resistor, that goes way down because the current goes way down. So one way to rectify this would be to go out and buy an inverter, convert this to AC, and then put a transformer to step the voltage way up.
And then do you have to dump it back to DC when you get to your pump?
Well, it would depend. I mean, if we were sitting here designing this from scratch, we would probably buy an AC pump. Yeah, we would buy an AC pump.
Then your inverter would be perfect.
Right. But do you see how you can use the various laws of electricity and Ohm's law and series circuits to figure out, what am I going to do here? What's the best way to go? Let's say that you have a contracting business. Somebody comes to you and they say, hey, I've got a lot of money invested in solar panels. And those things are putting out more energy than I can use in my house. And I would really like to use the solar panels to drive this water pump. Okay? Can you make that happen for me? Well, if you're smart about it, you're going to sit down and you're going to analyze how efficient that system would be. And then you're going to come back to the owner and say, agreed, you have a lot of excess power in your solar panels. But to use it to drive a water pump that's 2 miles down your property is going to be a highly efficient utilization of that energy. You might want to build a swimming pool or put in a jacuzzi or something else that would require energy that would be closer to your solar panels and thus more efficient. This way, you're wasting, you know, over 1/3 of your energy in just getting it to the pump. Why do you want to do that? Okay, that's the why and the how that we study this stuff. It's because we can come in to a job and there can be, you know, 5 different options. Should we use AC? Should we use DC? Should we use transformers? Should we use inverters? Should we use this, that, whatever? Should we use an AC pump, a DC pump? Should we use a DC pump with an inverter? Should we, whatever. We can figure out which one of the scenarios will cost our customer the least amount of money in electric bills. And also in maintenance and repair and stuff like that. Okay? All right. Any questions? Does this make sense? Are you guys able to follow this, or did I go too fast? Guys and ladies? Okay. Well, see, now you can watch the tape about 15 times. I'm kidding. You can watch the tape, and then you can go, and then the light will go on. You'll be like, oh, I got it. Okay? All right.